Organs. Definition. An organ is a part of a living body that performs certain important functions. Examples of organs are eyes, nose, ear, tongue, and skin.
Location. The heart is located under the rib cage to the left of the breastbone or sternum and between the lungs. Cool facts. If all the blood vessels in our body were laid end to end, it would stretch almost 3 times around the widest part of the earth. Your heart is about the same size as your fist. During an average lifetime, the heart will pump nearly 1.5 million gallons of blood, enough to fill 200 trains tank cars. A woman's heart typically beats faster than a man's heart. The heart of an average man beats approximately 70 times a minute, and a woman's heart beats 78 times a minute. The heart is made of strong muscles, which pushes almost 10 pints of blood through our blood vessels every minute. Blood travels from our heart to every part of our body and back again. Blood leaves your heart through a big artery called aorta, which branches many times into smaller tubes or vessels. As the blood squeezes through the tiniest vessels of all, called capillaries, it delivers oxygen and nutrients to the cells. It collects carbon dioxide and waste. The vessels get wider again and become veins, which join together and go back to the heart. What does it do for us? The heart pumps the blood. Each time the heart beats, it squeezes blood down tubes or vessels that carry it to every part of your body. The blood picks up and delivers oxygen, food, and waste to many different cells in our body. How to keep the heart healthy. Cut down on salt. Too much salt can cause high blood pressure, which increases the risk of developing heart disease. Physical exercises keep the heart strong. If you smoke, you are twice as likely to have a heart attack. 30 minutes of moderate exercise a day will keep the heart muscle fit. Don't eat junk food. Eat fruits and vegetables. Research on your own. What are the chambers of the heart called? How do you measure the heart rate? What is high blood pressure? What is a pulse? What controls your heartbeat? Why does the heart beat faster when you run? What is a heart murmur? What problems can a heart have? One of the most common heart disorder in adults is coronary artery disease, caused by fat deposits, calcium, and dead cells. This condition is called atherosclerotic plaques, which forms on the inner walls of the coronary arteries, or the blood vessels that supply the heart. These interfere with the smooth flow of blood to the heart. Congenital heart defects are abnormalities in the heart structure at birth. If blood flow to the heart stops, heart attack can occur. This damages the heart muscle due to lack of oxygen. An arrhythmia may cause the heart's rhythm to be irregular, beating fast or abnormally slow. Arrhythmias can occur at any age and can be treated.
Organs of a human. The organs in our body form systems to allow life processes like movement and reproduction. Our body has various organ systems. Each system performs its own function, but they all work together to keep us alive.
Levels of organization. When building a city, you start with bricks. Many bricks joined together makes a wall. Walls working together make a building, and many buildings complete the city. The human body is put together in a similar way. Humans start with cells. Many cells joined together make tissue. Tissue working together make an organ. And many organs make an organ system. Cells are the smallest living part of an organism. Some examples of cells in the human body are brain cells, lung cells, and bone cells. When cells of similar structure and function join together, they form tissue. A group of brain cells is called brain tissue. A group of lung cells is called lung tissue. And bone cells joined together is called bone tissue. When a group of tissues that perform a specific function join together, they form organs. Brain tissue comes together to make your brain. Your brain is an organ. Lung tissue comes together to make your lungs. And bone tissue comes together to make individual bones. An organ system is a collection of organs working together to perform jobs. Your brain is a part of the nervous system. Your brain, spinal cord, and nerves work together to collect and process information. Your lungs are a part of the respiratory system. Along with the diaphragm and others, they help you breathe. All of the bones in your body are a part of the skeletal system. Bones, cartilage, ligaments, and tendons give your body structure and support. So from smallest to largest, your body is made up of cells, tissue, organs, and then organ systems. These are the levels of organization.
The digestive system. Major organs and their functions. Mouth. Chew and grind up foods, saliva also begins the chemical breakdown. Esophagus. Pipe connecting mouth to stomach. Stomach secretes an extraordinarily strong acid pH equals 2 that leads to breakdown. Pancreas produces the hormone insulin that regulates blood sugar level. Liver produces bile which breaks down fats in foods.
Hi, I'm Sarah and welcome to the Nerd Circle. Today we're talking about the functions of the organs of the digestive system. The tongue. The tongue is an organ. The function of the tongue is to help move the food around your mouth. The tongue allows you to swallow and is able to coat the food with saliva, enabling the food to be better digested in the stomach. The pharynx and the esophagus. The role of the pharynx is to send food to the esophagus and air into the lungs. The esophagus undergoes a process called peristalsis. The muscles in the wall push liquids and food down into the stomach. Peristalsis is muscular contractions and relaxations, which push fluid forward. The liver. The function of the liver is to produce bile, which is a substance that breaks down fat. The cells in the liver contain enzymes that break down the food we consume. The stomach. The stomach's main function is to accept and then store the food. When the food enters the stomach, the glands produce stomach acid, which breaks down the food even further. Then muscles in the stomach move acid and food around, and the acid is able to kill the bacteria that were consumed through either food or saliva. The gallbladder. The gallbladder's function is to store the bile, which is produced in the liver. The bile becomes more concentrated and more powerful in its ability to do work whilst it is stored in the gallbladder. When fats arrive in the small intestine, it is the gallbladder's job to release the stored bile, which helps break down the fats. This also counteracts the acid in the food arrived from the stomach. The pancreas. The pancreas has two major functions. The hormones made by the pancreas balance the blood sugar level. The pancreas also contains digestive enzymes that break down the carbohydrates, fats and proteins. The large intestines. The function of the large intestine is to reabsorb water and balance the amount of fluid in the body. It also absorbs vitamins, stores the waste and processes fiber. The small intestines. Another organ is the small intestine. Its function is to absorb most of the nutrients within the food we consume. The food breaks down into a liquid and, as it comes in contact with the blood vessels, the blood leaves the small intestines. The blood carries nutrients, minerals, etc. to the body. So that's all we have time for today. Tune in next time for another great report on body systems. Thank you and good night.
The respiratory system. To provide the body with a fresh supply of oxygen for cellular respiration and remove the waste product carbon dioxide. Major organs are nose, larynx, trachea.
Hi, it's Mr. Anderson, and welcome to my podcast on the respiratory system. Function of the respiratory system is basically to take in oxygen and then get rid of carbon dioxide. And right here in Montana at around 5,000 feet, that's no big deal. But if I were to climb Mount Everest, the higher I go, the less oxygen there's going to be. And that's a real limit to our ability to climb very high. And so it wasn't until 1953 that Sir Edmund Hillary and Tenzing Norgay finally climbed Mount Everest for the first time. And you can see Tenzing Norgay right up on top, the first photo ever taken from the top of Mount Everest. It wasn't until 1953, but if you can't see on his back, there's a huge canister that contains oxygen, and that leads into his mouth because they had to take oxygen with them. And so it wasn't until, I think, 1971 that somebody was able to climb all the way up Everest without using oxygen. And that they do that by going up to a base camp, move up higher, move down, move higher, move down, move higher, move down. And so their body's starting to accommodate to that change in the elevation. And even that, you're pretty much dying at the top because of that lack of oxygen. And so basically, animals have figured this out in a number of different ways. If you're a worm, your respiratory surface is actually going to be your skin. You're absorbing oxygen and getting rid of carbon dioxide through your skin. So their skin has to be moist, and they have to have a large surface area. If you're an insect, you use things called spiracles. So basically there are holes on the side of an insect that go to tubes, that go to more tubes and more tubes and more tubes and more tubes. And an insect actually has tubes that almost go all the way down to the level of cells. And so you have to have a huge surface area is one thing you need, and then it has to be moist is another thing you need. And so the two big things I want to talk about are gills. So gills is a way that fish have solved this problem. And then lungs, and that's the way that we've solved it. And so what's the difference between fish and us? Well, fish live in an area that's really, really moist, so they don't have to worry about that. And so their gills just sit right out in the water. But they also live in an area where there's not much oxygen at all. And so they have to have a very efficient way of exchanging oxygen. Us, well, we have to fold our lungs inside our body so we can keep them moist. But there's so much oxygen in the air relative to the amount that's in the water that we don't have to be as efficient. So how efficient do the gills actually have to be in fish? They can reclaim something like 80% of the oxygen that's in the water. So they're really, really efficient. We're not even close to that. And the way they do that is they use something called countercurrent gas exchange. And so basically, as the blood flows through the gills, the blood is going to flow like this. So all the blood is going to flow in this direction, and then it's going to flow out the other direction. So in the gills, it's going in that direction, and then it comes out in the other direction. But the water is going to flow in this direction. And so what you have is the blood flowing in this direction, and then you have the water flowing counter to that. And so as they go like that, it pulls water in over their gills, but the blood is moving in opposition to that. Engineers use countercurrent exchange quite a bit, but basically what is it doing? Well, if you think about this is going to be the dirtiest of blood down here, and then it's going to get cleaner and cleaner. In other words, it's going to get more and more oxygen. But what it's doing is, as it gets more and more oxygen, it's meeting water that's more and more fresh, or in other words, it has more of the oxygen present. And so by putting blood in the opposite direction, they're really efficient at getting that oxygen outside of the water. Now us, we don't have that problem. We do have a problem with moisture, and so we actually have to fold our gills inside our body. They're not gills, but we fold our lungs inside our body. And so we have a trachea that leads down into bronchus and then bronchioles all the way down into the alveoli. One thing that's important to note is that it goes in, and then that's it. In other words, it's one-way flow. When we breathe in, goes in, and then that's the end of it. And so if you take things in, like if you smoke, all the material that comes in is going to go into your lungs, and then there's no out. And so if you breathe a lot of coal dust, it's going to go in, and then it gets stuck in there. Or asbestos goes in and gets stuck. And so the lining of the trachea, lining of our respiratory system, have these cilia on them. And so basically what happens is those little hairs are going to move material out of your body so you can cough it up and eventually swallow it. Another cool thing about this is that it really looks, let's even go to this level, it almost looks like a tree upside down. And so basically what's happening is that we are increasing the surface area by having the trachea go to the bronchus and then the bronchioles, and then they just keep branching and branching and branching. Again, why are they doing that? They're doing that to increase the surface area. And so your lungs are small, but I remember once reading that they have the surface area of a tennis court. And so by having that large surface area, we can absorb even more oxygen. But the functional units of the lungs are the alveoli. So if we get way to the end of these tiny bronchioles, we eventually have these little sacs. They're called alveoli. They're covered in a single layer of cells called simple squamous cells. And they have a tendency to just kind of fold in. Imagine a tiny balloon that's that small, it would just kind of fold in on itself. And so they have to have these chemicals called surfactants on the inside that kind of lubricate it so it doesn't close up. That's one of the reasons why premature babies have to be in a ventilator, because they haven't really developed that surfactant yet. But wrapped around all the alveoli we have these capillaries. And so basically what's happening is that we're taking oxygen from the alveoli, and we're passing that off onto these capillaries, and then we're getting rid of carbon dioxide. That's the function of the alveoli. Now, how does breathing occur? Breathing occurs using the diaphragm muscle. You've dealt with the diaphragm if you've ever had the hiccups, because that's just a spasm in the diaphragm muscle. But basically what happens is we have the diaphragm muscle here, and then as that contracts and pulls down, then we have air moving in. So it's like you had a jar with a balloon on the inside of it with rubber on this side. And if I were to pull right here, if I were to pull that down, basically it's going to inflate the balloon because air is going to move in through here. So I decrease the pressure. And then as I relax the diaphragm, it's going to go like that. And as I contract the diaphragm, it's going to move up like that. It's very important that then, just like this jar, that this is very intact here. We have to make sure that this whole thoracic cavity is intact so we can create that pressure. Okay, so let's get to the level of that oxygen exchange. So how do we get oxygen in? Well, basically, if you were to look here in the capillaries, let's imagine that this out here is the space in the alveoli. So now we have air coming in, so we have air out here. Basically what's going to happen is these red blood cells, as they move through the capillaries, that oxygen that's inside the alveoli is going to move in. And so these red blood cells are almost in direct contact with the capillaries. Now where is the oxygen going to be stored? We have a chemical called hemoglobin. Hemoglobin is a protein, and that's stock full inside of all of our red blood cells. That's why it's red. So basically, inside the hemoglobin, we have these iron molecules, one there, one there, one there, one there, and that iron is going to bond to the oxygen that's found inside the air. And so why is it red? It's because it literally is rusting. The oxygen is attaching to the iron, and it's giving off that red color. And so that's where the oxygen is going to bind. It's going to bind to that heme group, or the iron inside the hemoglobin. What about the carbon dioxide? Well, the carbon dioxide is not really contained within the red blood itself. Basically what it's doing is it's being converted to bicarbonate. So we're converting that carbon dioxide with water to this bicarbonate, and a lot of that bicarbonate will actually be right here inside the plasma of the blood. Some of it will be in the blood cell, but most of it's in the plasma. When we get here to the alveoli, we've got enzymes that control all of this, then that's going to release as carbon dioxide. So carbon dioxide goes back into the alveoli, and we breathe that out. We take in more oxygen over and over and over again. And so that's the respiratory system. It doesn't work if we don't have the circulatory system, but we'll get to that in the next podcast, and I hope that was helpful.
The excretory system, major organs and their functions. Kidneys. The main organs of the excretory system, rectum. Solid food waste travel out of the body through the rectum. Skin. Sweat glands remove excess water and salts from the body. Lungs. Expel the waste gas carbon dioxide.
Excretory system. Just as how we throw away the waste material from our homes, our body too has a system to remove the waste. This system is called the excretory system. The excretory system consists of kidneys, ureters, the urinary bladder, and urethra. The main organs of the excretory system are the kidneys. These are two bean-shaped organs located on each side at the lower abdomen. The kidneys filter the blood. They help to get rid of waste in the form of urine. The urine is carried by tubes called ureters to the urinary bladder. The urinary bladder stores the urine. When the bladder is full, the urine is passed out through the urethra. In this way, the excretory system removes waste from the body. A detailed anatomy of the kidney is shown here. The longitudinal section of the kidney shows the location of the renal cortex, renal medulla, the renal pyramid, and the renal pelvis. Observe the placement of nephrons in the enlarged renal lobe. Seen here is the anatomy of a nephron. A nephron is also called as the kidney tubule. It is the basic unit of a kidney. There are more than 1 million nephrons in a kidney. The main parts of a nephron are the Bowman's capsule, the glomerulus, the proximal convoluted tubule, the distal convoluted tubule, and the loop of Henle. An enlarged view of the Bowman's capsule with the glomerulus may be observed here.
The circulatory system, major organs, heart, the major muscle of the circulatory system. The nervous system, major organs, brain, control center of the body where all the processes are relayed through. A skeletal system supports the body and keeps it in shape.
Skeletal system. Head and neck. The skeletal system of the head and neck plays an important role in protecting the brain and all of its attachments that get sent throughout the rest of the body. The head and neck make up the top portion of the axial skeleton. The skull is the bony section of the head and consists of cranium and facial bones. The skull encases and protects the brain, houses the brain senses, provides attachments for muscles of the head and neck, and helps to form the first portions of the respiratory and digestive tracts. Spine. Stretching down the midline of the trunk from the base of the skull to the coccyx, the spine plays an extremely important role in our bodies, as it supports the upper body's weight, provides posture while allowing for movement and flexibility, and protects the spinal cord. Chest and upper back. The skeletal system of the upper abdomen surrounds important organs such as the heart, lungs, and others above the diaphragm. The portion of the spine in the upper abdomen is made up of bones, called the thoracic vertebrae. These are the 12 vertebrae in the chest area. They have facets on the sides of their bodies that join with the ribs. Shoulder joint. The shoulder joint is actually made up of two separate joints, the glenohumeral or shoulder joint, which is formed by the articulation of the rounded head of the humerus, or upper arm bone, into a cup-like depression of the scapula, called the glenoid fossa. The second is called the acromoclavicular joint, and is formed by an articulation of the lateral clavicle with the acromion process of the scapula. Humerus. The humerus is the bone of the upper arm. The smooth, dome-shaped head of the bone lies at an angle to the shaft, and fits into a shallow socket of the scapula, shoulder blade to form the shoulder joint. Below the head, the bone narrows to form a cylindrical shaft. It flattens and widens at the lower end. At its base, it joins with the bones of the lower arm, the ulna and radius to make up the elbow. Radius. The radius is the shorter of the two long bones of the forearm. The other is the ulna. The radius is the bone on the thumb side of the arm. The shaft of the radius has a broad base that joins the lower end of the ulna and the upper bones of the wrist at a large process called the radial styloid. The disc-shaped head of the radius, which is smaller than the base, joins the lower end of the humerus bone in the upper arm to form the elbow joint. Ulna. The ulna is the longer of the two bones of the forearm, the other being the radius. When the palm faces forward, the ulna is the inner bone, the one nearest the body running down the forearm parallel to the radius. The upper end joins with the radius and extends into a rounded projection that fits around the lower end of the humerus, the upper arm bone to form the elbow joint. The lower end of the ulna is rounded, and forms a joint with the wrist bones and lower end of the radius. Hand and wrist bones. The hand and wrist bones allow movement, so that the body can manipulate objects. On the radial shaft of the smaller forearm bone, just below its head, is a process called the radial tuberosity. It serves to attach the biceps brachii muscle, which bends the arm at the elbow. At the lower end of the radius, a lateral styloid process provides attachments for the palmar radiocarpal ligament on the palm of the hand and the dorsal radiocarpal ligament on the back of the hand from the radius into the wrist. Pelvis and lower back. The skeletal system of the lower abdomen, including the pelvis, helps protect the spinal cord, digestive and urogenital systems and other internal organs such as the bladder, rectum, and in women, the uterus. The skeletal system of the lower abdomen includes the 5 lumbar vertebrae in the small of the back. These vertebrae support more weight than the vertebrae above them. At the base of the lower spine is a large triangular bone called the sacrum. Its narrow lower part joins the coccyx, or tailbone. The sides of the sacrum are connected to the iliums, the largest bones forming the pelvis. The iliac crest forms the prominence of the hip. The pelvis is a ring of bones in the lower trunk of the body, which is bounded by the coccyx, tailbone and the hip bones. The pelvis is made up of 3 hip bones, which are joined by rigid sacroiliac joints to the sacrum at the back. The hip bones curve forward to join the pubic symphysis at the front. It is significant during childbirth, as it is capable of stretching to permit delivery. Leg and foot. The skeletal system of the lower extremities includes the legs, feet and toes. This subsystem supports the muscles that help with running, walking, standing and more. The weight of the body is transmitted to the legs through the pelvic girdle at sacroiliac joints. These joints, along with the ligaments attached to them, anchor the lower limbs to the axial skeleton. Tibia. The tibia is the inner and thicker of the 2 long bones in the lower leg. It is also called the shin bone. Its upper end is expanded into medial and lateral condyles, which have concave surfaces and unite with the condyles of the femur. The tibia is the supporting bone of the lower leg and runs parallel to the other, smaller bone, the fibula to which it is attached by ligaments. The front of the tibia, or tibial tuberosity, lies just below the skin and can easily be felt. Fibula. The fibula is the outer and thinner of the two long bones of the lower leg. It is much narrower than the other bone, the shin, to which it runs parallel and to which it is attached at both ends by ligaments. The upper end of the fibula does not reach the knee, but the lower end descends below the shin and forms part of the ankle. Its main function is to provide attachment for muscles. It doesn't give much support or strength to the leg, which explains why the bone can safely be used for grafting onto other bones in the body. Ankle and foot bones. The ankle and foot bones begin at the end of the tibia and fibula, at a synovial hinge joint. The lateral malleolus is joined to the ankle by the anterior talofibular ligaments, and the posterior talofibular ligaments. These ligaments form a prominence on the side of the ankle.
The skeletal system purpose to provide structure and support to the human body. Bones are where new blood cells are generated. Major bones of the human body: femur, thigh bone, radius and ulna, lower arm, etc. The immune system to remove infectious diseases and other pathogens from the human body. Skin, also called integumentary system. The skin is the body's first line of defense.
Welcome back, friends. In this video we'll be talking about the organs of the immune system. Especially we'll be talking about the organs where our all the immune cells or killer cells or sometimes helper cells that we have talked before, that lymphocytes and also other types of myeloid progenitor cells will develop, and about those homes and the training centers where all of them are trained for the purpose of serving our body when the pathogen attack us. Okay, so let us look at it. Now, if we look at the organs of the immune system, we can divide it into two parts. One is the primary organ system, another one is the secondary organ. Now, the primary organs are the most important parts. So let me take a color. Okay. Now, the primary organs are huge organs or larger organs where we are having most of our immune defense soldiers to be produced, and those organs are thymus and bone marrow. These two regions are the primary organ of the immune response or primary immune organ in our body. Now, thymus will be seeing each of these organs and the architecture of the organ in later videos, in later slides, sorry. Now, secondary organs are not that much important. They are not chief organs. Rather, they are helping to establish the total immune response inside our body. So they are helping these primary organs for establishing the function. So these are called the secondary organs. Like lymph nodes, we are having spleen, mucous and also mucous and lymphoid tissues, and different associated lymphoid tissues. Now these tissues are not exactly among the lymphatics, but this is a coat of mucus having the lymphoid tissue, and they are called mucus associated lymphoid tissue. Okay, and we are having different type of lymphoid associated lymphoid tissues like gut associated lymphoid tissue. Then we are having so it will be called GALT. We are having different regions. Okay, so these lymph nodes and spleen and these organs, these are the secondary organs. They are helping thymus and bone marrow for producing all the immune response soldiers to protect our body. Let us first talk about the morphology of thymus. Now you can find here the thymus excuse me, thymus present here in between this place, right behind our heart, in between the two lungs. This is the organ thymus. Okay. Now this thymus is having the structure like that. Now in this structure we can find there is a coating region outside which is called the capsule, and all we are also having different segmentation inside them. Okay, now if we zoom into a particular segmentation, here we can see in this particular segmentation we will see different or distribution of cells. Now in this particular tissue we can find a very important architecture, and the architecture is that we are making a network with the help of two different kinds of cells. Especially they are called the epithelial cells. Okay, so they are called the epithelial cells in both the type. Okay, but this epithelial cell, depending upon the presence, will be called cortical epithelial cell and medullary epithelial cell, because at the terminal part of this or the part which is pretty close to capsule is called the cortex of this thymus or cortex. So in this cortex part the epithelial cells are present. They are called the cortical epithelial cells, and those which are away from the capsule, and at the central region of the thymus cross section, it is called the medulla region. So the epithelial cell presents there are called the medullary epithelial cells. Both of the cells can be visualized in this picture pretty clearly. Cortical epithelial cells are colored in blue, medullary epithelial cells colored in orange or red, whatever. Now we can see in the cortical epithelial cells and also in the medullary epithelial cells, the cells are looking like dendritic cells. So they hold on to itself, they hold on to each other to make a network, to make a mesh-like network, and this network will contain several gaps, several regions, and these regions will be regions are for the attachment of other cells like macrophages, dendritic cells, and Hassel's corpuscles, and all these different types of cells. Okay, now in case of cortical epithelial cells we are having much more tighter arrangement of these epithelial cells, and in case of medullary epithelial junction we are having the cells which are less tightly packed. Okay, now in case of cortical epithelial cell, in the middle portion of this cortical epithelial cells we are having small blue colored cell, as you can see here. They are called the thymocyte or lymph node for a longer time. Now B cells and T cells, both of the cells are of two different types. One is a normal type of cell, another one is memory cell. So if you look at the B cells, which is the general cell or normal cell, they can go and reside into the germinal center region for the maturation. After the maturation, they will leave from this place. Okay, but if you are dealing with the cells, B cells, which are memory cells, then they must go and sit onto some region of this lymph node for longer period of time, because memory cells are having the work for having the memory for a particular pathogen infection, that if in future that pathogen re-enters the body they can fight against the infection, right? So here again, so this is how the cells start to mature, and these are the regions. So when they need to be removed from this lymph nodes, what they can do, they can go easily from the efferent lymphatic vessel. So remember here, there is a place for entering, so this is the place for entering, and this is the place for exit. Okay, so this is place for entering, this is the place for exit. So this is not a single way system, it's a two-way system. So you can also find this valves here. You can also see this, these are the valves. Now these valves are present and they can be opened into only one direction, so no cell can enter into this lymph node via this process. You cannot enter here via this direction. Only way of entering into this lymph node is via this afferent lymphatics, which are larger and present in higher amounts comparatively to this efferent vessels, because efferent vessels are less present in less amount. Now in each of these lymph nodes we are having this capillary and venule present here like that. Okay, so both of them, they are not blood vein or blood capillary, they are lymphatic artery and lymphatic veins. Remember, again according to the name, lymphatic artery means they are carrying cells, lymphatic veins when they are carrying they are making them out of this lymphatic system. Okay, this is how the whole process is organized, the whole morphology is organized. Now for example, if I give a real-time example of how or what happens to this lymphoid tissue and lymph nodes when a pathogen enters into our body, it can give you a clear understanding. For example, say this is a bacterium which can come and attach to our epithelial cell, then what will happen? Local infection can cause. So this is the infection or injury. Through this injury cells start to enter and invade into our tissue. Now where we are having the killer cells like macrophages and dendritic cells, the antigen presenting cells. They can come. These are the phagocytic cells. Remember, so they can come and engulf bacteria. They can chop up the bacteria and can hold on to a piece of the bacterial sample onto their surface. Now they need to show this to other members, right? So they will come and invading through the afferent tube of the lymph node, lymphatic system. They will come to the lymph node into the germinal center. At this part, we are having all the cells, B cells and all cells waiting there. So they'll show to all of these premature B cells that like, look what I've got, right? These are the bacteria. So we need to design something which can go against this bacterial pathogen. So those cells start to produce the important machinery to go against those bacterial pathogens that are shown by these dendritic cells and macrophages. Okay, so these cells will start to produce, so B cells will start to mature, and after some time those B cells will be matured into called large plasma cells. Now these plasma cells are pretty large and they will produce a lot of protein molecules called antibodies or immunoglobulin. Remember, I've talked it before, they can produce Ig or immunoglobulin or what is called the antibody. That means they can go against the antigen or piece of bacterial pathogen. Okay, so again when they are produced for a particular sensitive antibody against that pathogen which enters, they'll leave through the efferent system and finally they will reach into the tissue where the pathogen invaded. Now there they will sit onto there. I can release all those immunoglobulin. Or another thing can happen. They can sit onto this lymph node and they can release their weapons like immunoglobulin. So their weapons will be moved from through this efferent lining, and it can go to the invading tissue, and it can go and hunt all those bacteria and kill all those bacteria in a moment. Okay, so this is how whole system can work. Okay, and the second part of the discussion, what I've called that the production of the antibody and killing it is called the adaptive immune system, because in this case we need to rely upon both of the cases, like production of antibodies. But there will be another mode of immune system where you will only rely on cells like T lymphocytes and cytotoxic cells and natural killer cell to kill cells. It will be called the cellular mode, but this mode is called the humoral mode of the immune response. Okay, so this is how the whole process work surrounding this lymph node. Okay, so there is another many round of defense that can be carried out against the infection or invading organism, but we haven't talked about them because we don't need to tell it in according to the feature of this lymph nodes. But lymph node is in the part of the detection and the production of this. Okay, so that's why I've shared it with you. So now this is another secondary lymphatic system. It is called a spleen. Now spleen is having two structures, like again it is having a capsule and then it is having a medulla region like that. Okay, now this is having two different parts. One is a red pulp and one is the germinal center and the middle region, okay, or white pulp. In the white pulp region, it is having two different regions, primary follicle and secondary follicle. Again, primary follicle means a small cell surrounding and making a center. The center will be called the germinal center. So all of these things remain the same. So primary follicle surrounding small cells and it will produce a center which is germinal center. This germinal center cells start to mature. Cells like B cells, T cells start to, in this case B cells start to mature, and those cells can be, they are matured into, they can be matured into the plasma cells and they can start producing antibodies. Remember, we have talked before about the other lymph nodes. Okay, but in this case we are having artery and venules because this is also a part of our blood vessel system. So that's why we can find a red pulp region there, because red blood cells that is coming out through these arteries can go to this peripheral region. This region is filled with those red blood cells. That's why they are called the red pulp region. It will look like much more red, but all the other region, this middle region will look much less red. So that's why we call the white pulp. But this, believe me, this is not actually white. Okay, So anyways, the basic construction remains the same. So it is having a primary follicle inside it, then germinal center. In the germinal center we will have the maturation of the B cells into the plasma cells, and they can produce antibodies to fight against infections. But the exception about the spleen with other lymph nodes is that spleen is much more bigger, and it is having a vein and artery system. Okay, and the vein artery distribution there is called the helium, as you can see in these cases. Okay, and it is having two different regions, red pulp and white pulp accordingly. So uh, I hope this is the end of the different organs we have talked about. I hope this is helping me. Thank you.
The endocrine system to control growth, development, metabolism, and production through the production and secretion of hormones. Major organs: hypothalamus, pituitary gland, thyroid, parathyroid, adrenal glands, pancreas, testes, ovaries. The muscular system works with the skeletal and nervous system to produce movement, also helps to circulate blood through the human body.
The musculoskeletal system. The musculoskeletal system is responsible for the mechanics of movement in the body and consists of bones, joints, and muscles. There are 206 different bones in the human skeleton that are made up of calcium, phosphorus, other mineral salts, and some organic substances. The vertebral column is composed of 24 vertebrae, the sacrum, and the tailbone. The vertebral column is designed to support the body and the internal organs. It also serves as protection for the spinal cord, which is the central communication cable from the brain to the rest of the body. The skeleton is the framework which supports and protects the soft tissues and organs of the body. It provides attachment for tendons, muscles, and ligaments which move the body and serve to protect certain vital organs. The skull is a group of bones which fit together to encase and protect the brain. It also forms the framework for the face. The rib or thoracic cage supports the shoulder girdle and arms, protects the internal organs in the cavity, and plays a part in breathing. The pelvis protects the lower abdominal and internal reproductive organs. Because the bones are linked to each other and act together, body movement is made possible. However, no motion would be possible if it were not for the joints. Wherever two bones are attached, a joint is formed. Immovable joints are in the skull. Slightly movable joints are between the vertebrae of the spinal column, and free movable joints are in such places as the knee, shoulder, hip, and elbow. Ligaments join bones together and keep them from getting out of place. The muscles are a bundle of fibers which have the property of contracting and relaxing. This produces motion. In man there are more than 500 muscles, and if it were not for the muscles, the body could not move. There are two types of muscles, involuntary and voluntary. Involuntary muscles, which can be found in the heart and the digestive system, function automatically. The voluntary muscles, such as the bicep and tricep, are under our control. Mechanically, the muscles can exert force and do work only by pulling, not by pushing. To restore a muscle to its original position to work again, it must be pulled back into position. Consequently, muscles work in opposing groups, one of which reverses the action of the other.